Hey everyone, I am Duo Zhang from NYU Courant Institute, the Computer Science Department. And today I'm gonna represent myself and my partner Zhiliang Chen to give everyone of you a presentation about logarithmic regret algorithms for online convex optimization. So first of all, I want to talk about the motivations about why we want to have this kind of algorithms. So the first thing I want to mention is all the previous approaches covered in our lectures for online convex optimization are based on the first order of optimization method. For example, the online gradient descent, right? And these optimization methods use only the first order derivatives of the payoff functions. And the regret achieved by these algorithms is proportional to a polynomial in the number of iterations, namely its square root of capital T, and the capital T here is the total number of iterations. So in addition to the general frameworks, there are some specialized algorithms which requires very strong assumptions and are able to attain regret proportional to the logarithm of the number of iterations. But in general, in practice, we are not gonna always have some situations or objective functions that satisfy our rules, all these rules and requirements. So the motivation comes from here. Can we find some optimization algorithms that may have better regret bound and in the same time has less assumptions, have weaker assumptions? So for example, the online gradient descent method. We have talked about this in the lecture, so I won't spend so much time on this. Briefly speaking, you have to give an initial guess of the solution of the optimal point x1 to the algorithm, and for every iteration, the algorithm will do a gradient descent step, and if the gradient descent after the gradient descent the resulting point is not in the constrained convex set P, we have to project it onto the nearest point in P, and the project process is denoted by a capital pi sub P, and the distance used in the projection process is Euclidean distance. So when the objective function, I want to say that if the objective function for each round ft is the alpha strongly convex function, we can have a logarithmic upper bound of OGD, and if we don't have this assumption, it's nothing. The upper bound of the regret is still square root of capital T. So that's a precise example of what I just said in the motivation part. So there are two basic methods in mathematical optimization problems. The one is gradient descent method, and the other one is Newton method in optimization. So when we want to find something better, we discovered the Newton method in optimization, and can we have a try on that? So in case some of you are not familiar with Newton method in optimization, I want to give a brief introduction of it. So I want to minimize the convex function fx, and the way to do it is to iteratively find the solution for the gradient of fx to be 0. And the updating rule here is actually xk plus 1 equals xk minus the gradient at fxk over the Hessian matrix of fxk. So it is actually a Newton-Raphson method applied on the equation, the gradient of fx equals 0. And and they have a big difference in the convergence rate with between gradient descent method and the Newton method. So the gradient descent method converges linearly or sublinearly. I won't prove these conclusions here. I only provide them. So and the Newton method converges quadratically, which is way much faster than gradient descent method. Since the Newton method in optimization has such an advantage over the gradient descent method, I want to ask, can we do more with the Newton method? So the answer is yes, and I want to present you guys a new algorithm, the online Newton step algorithm. So basically, it is the whole structure of the algorithm is very similar to the online gradient descent method. However, the only difference here is the updating rules changed. The updating rule here is actually use the Newton step to update xt minus 1 and project it with respect to the distance, use the distance with respect to matrix at minus 1 instead of the Euclidean distance to the nearest point in convex set P. And here I want to mention is the nabla tau is actually the gradient or the Jacobian matrix of objective function at around tau, and matrix AT is actually the sum of the product of Jacobian I times Jacobian I transpose from round 1 to round t plus some residue epsilon times the identity matrix. In here is the matrix A sub t is actually a very good approximation of the Hessian matrix of all the objective functions of all rounds. So especially when all the objective functions becomes a linear least square problem, and A sub t is actually a very precise approximation of the Hessian matrix. So guarantee for online Newton step algorithm, and the upper bound of the regret of an ONS algorithm is actually less than 5 times 1 the sum of 1 over alpha plus GD and then times n log t. The one thing I want to mention here, the only assumption in this guarantee is actually for the ft, the loss function ft at each round. The loss function is actually a alpha exponential concave function. And the proof, as for the proof, it is very long and complicated in the original paper, so I won't spend too much time on this. If you want to see the exact proof, please go through and find it in the original paper. I will go through the proof very quickly. So I will start the proof with a lemma here, and actually this lemma is actually a Taylor expansion at point y for function f, and you can conclude this inequality with a Taylor expansion, and then you can define the point just updated by the Newton step without projecting back to the convex set P as yt plus 1, and you can also denote the point after projection as xt plus 1. So by the definition of ft, and it is actually the Newton step updating rules. So if you subtract x star on both sides, you can get equation 1, and then you multiply matrix A sub t, the Hessian matrix A sub t on both sides, you can get equation 2, and then you multiply the transpose of 1 by 2, you can get the equation 3. And here I want to mention that on the left hand side of the equation, it is actually the distance between t plus 1 and x star with respect to matrix A sub t. and that's why we use the distance in the projection. We use the distance with respect to matrix A sub t in the projection process instead of the Euclidean distance. And then use a very important property of projection for convex set P, which is, I won't prove it here, but you can see it very intuitively. The yt plus 1 is a point outside convex set P, and x star and xt plus 1 are two points inside P. So the distance between yt plus 1 and x star is actually can be larger than the distance between 2 points inside the convex set, right? So combining this property and equation 3 and the lemma at the beginning, we can sum them from round 1 to round capital T. We can have inequality 4 here, and if we use the fact that a sub t minus a sub t minus 1 equals the products of two Jacobian, then we can have then transferring the last term in the right hand side, this term to the left hand side, then we can get the expression for the sum of RT from round 1 to round capital T, as here. So we can now use the fact that A1 is actually A1 minus nabla 1 transpose equals epsilon times the identity matrix, and the distance between x1 and x star is actually smaller than the square of the diameter of the convex set P, and we choose epsilon as 1 over beta square d square, capital D square. We can get the regret upper bound as here. So with the lemma, I won't spend with the lemma here, we can substitute Vt as At and Ut as nabla sub t, and let R equals G, and we can get an upper bound like this. And now since we select epsilon to be equal with 1 over beta square d square, and we can beta equals the minimum, half of the minimum among 1 over 4 GD or alpha, so we can finally get the regard bound. So that's the whole proof of the guarantee of online Newton step. So now I want to talk about the implementation and running time analysis of the online Newton step algorithm. First of all, I want to say the exactation matrix here will not be calculated in the algorithm. Instead, an approximation of the Hessian matrix is used. So this approximation of Hessian matrix A sub t is the sum of Jacobian matrix I, the sum of the product Jacobian I times Jacobian I transpose from round 1 to round T plus some residue epsilon times the identity matrix, which is equation 6. And for each iteration or for each round, we have to calculate the inversion of the Hessian matrix for the Newton step. So directly calculating the inversion of the Hessian matrix is very time consuming. So here's a very quick way to iteratively calculate Hessian inversion for each round. So given that is equation 7. So according to equation 7, we can assign matrix A as A sub t minus 1, and for x we can assign it with the Jacobian matrix nebula T for round T, and we can compute the Hessian matrix, the inversion of the Hessian matrix A sub T in time of O n square using only matrix vector and vector vector products with equation 7. All right. So the next thing I want to talk about is follow the approximate leader algorithm. So we have talked about the follow the leader algorithm and the follow perturbed leader algorithm in our lectures. And these two algorithms uses the original objective function for each round, and they are trying to find the minimum of the sum of the original objective functions from round 1 to round t minus 1, and use this optimal solution as a for next round. And here we the follow the approximated leader doesn't use the original objective function for each round. Actually, it's a approximated objective function, which is a Taylor expansion for the second order Taylor expansion for the original objective function, and use now this approximated objective function becomes actually a sum of a quadratic function, which can be described as a least square problem here. So it's just the in the same form. It is in the exactly same form of a least square problem. So we can actually use a least square problem to approximate the sum of the original objective functions. So here is a follow the approximated leader algorithm. So the whole structure is still similar with the online Newton step algorithm or the online gradient descent algorithm. So the difference is here. Xt is solved by the by a minimizer. Actually, it is a minimizer. Xt here is a minimizer for the least square problem described before. And here A is not denotes the pseudo inverse of the matrix A sub t minus 1. So after we solve the linear the least square problem, we have to project the updated optimal solution to the convex set P. So it's still the same process. And here xt is actually the solution of the of equation 8, and while this sum being a least square problem. Okay. And so now I want to talk about the regret guarantee for the follow the approximate leader algorithm. So still we assume the objective function for each round is a alpha exponential concave function, and then the upper bound of the regret is given by 64 times the sum of 1 over alpha plus gd and times n times the sum of log t and plus 1. I won't provide the proof here because it's too long and too time consuming, and but what we can conclude here is we get a logarithmic upper bound again, and for the follow the leader algorithm, and it is beautiful since it transformed the optimization problem, which is equation 8, to a least square problem, and the result is much easier to solve. And the last thing I want to talk about in this presentation is actually exponentially weighted online optimization algorithm. This is covered in our previous lectures, and the upper bound of this is remarkable. You only have to require the objective function for each round ft to be alpha exponentially concave, and you can have a logarithmic upper bound for the regret, and it is upper bounded by 1 over alpha times n times 1 plus log t minus t plus 1. It is very remarkable. And as for the running time of exponentially weighted online optimization algorithm, actually you can approximate it by sampling points according to the distribution with the density proportional to WT, and then taking their mean. So use recent random walk analysis of Levolta and Van Pala's paper. M samples from such a distribution can be computed in time of tilde O, so n to the power of 4 plus n times n to the power of 3 and times log the capital R over little r. So now we have to conclude this paper, logarithmic regret algorithms for online convex optimizations. So basically the upper bound, we have discussed 4 algorithms in this paper, in this presentation, and with the relaxation of assumptions, the complexity of algorithm will gradually increase. So it is a good choice to choose the online Newton step algorithm with moderate assumptions, and ensemble complexity or its twin brother follow the approximate leader to obtain logarithmic regret bounds. Okay, that's the conclusion of this paperwork, and the regret bound and running time is listed in this table, and here for the time for the projection process, the time of the projection process is represented by T sub proj. Now it should be the end of our presentation today, and thank you for listening. Thank you. See you next time.